Hi guys, good afternoon, good evening.
Sir, good evening.
Yeah, good evening. Let's get started. So let me first quickly discuss about the assignment 1 that is assigned to you. Okay. I hope all of you are able to see the questions in assignment 1, and also you have installed MATLAB on your computers so that we can solve this. Of course, there are part of them. First two problems are hand calculations, and the last one is the third one is the programming part. So hand calculations is the first one is basically you are given a system of 3 equations, okay, and 3 unknowns. These are the equations that are given, and then you have to use the 4-digit floating point decimal arithmetic. Okay, so this means you can only keep 4 digits after the decimal. Okay, essentially you cannot keep another value after that, so you have to round off. So you can look at the 5th digit and then round it off. Okay, so for example, if we have 1.6666 like this, then you can only write it as 1.667. Okay, that is basically 4 digits. Similarly, if you have, let us say, 15,550 or 15,528, you can only write it as 1.553 times 10 to the 3. Okay, so that's what you can write it as. So that means you can only keep 4 digits at any instance, at any calculation. Okay, and then you proceed with that, and then with rounding. So that means we are going to look at the next digit, only the next digit, and then round it off. Okay, not the digits after that. So we are not going to come, even if there are multiple digits, we are not going to round it off from here and then come here. Okay. By Gaussian elimination without pivoting. The first one is without pivoting. So that means solve the system as it is. So formulate A, no need to do row operations, and then solve it. And then repeat part A using partial pivoting. So then the next one is part A. So again, do the same thing. Solve Gaussian elimination with partial pivoting. That means you're going to see at every step if the pivot element, you're going to look at the other values below the pivot element, and if they are going to be bigger than the pivot element, then you're going to do a row operation. You're going to switch the rows and then proceed. Okay, that's what you're going to see. Do for the first pivot, second pivot, and only the first 2 pivots. Okay, so that is the case. That is what you are going to repeat, and you will see if there is a difference. So verify that the exact solution above is, so the exact solution is given. Calculate the absolute error between the exact solution and those obtained in parts A and B. Okay, so you'll see that the solution you will get from the without pivoting and with pivoting would be different. Comment which of the two gives less absolute error. So you're going to compare the error. That means you're going to compare this with the other one after just to as would be done on a computer. Okay, so essentially you have to round it off to 4 significant digits. That's what you will do. And then when you calculate the error, you can either use some norm, or even you can calculate, this is the error vector. Okay, you can use some norm to report what is the error. Okay, or which is more accurate. I think it is easy to see. You can look at some delta x vector. Okay, which is for xy, x1, x2, and x3. Okay, any questions on the first problem? Will you be able to do? Okay, this is exactly like what we have solved in the class. Okay, the second problem is we are given a matrix A, and then A equals LU. So from Gaussian elimination and the multiplication factors. So essentially now calculate A equals LU from Gaussian elimination and the multiplication factor. That means you're going to arrange all the multiplication factors MIK into a lower triangular matrix, and then you're going to work with whatever is the upper triangular matrix U that you got. Okay, so that is your first way using Gaussian elimination. Second one is using the Doolittle's algorithm. That means you will decompose, you will write your L essentially as 1, 0, 0, and so on, L 2, 1, 1, 0, and so on. So you're basically going to write it like this, and then write your U, okay, which is going to be U 1, 1, U 1, 2, 0, and so on, U 2, 2, and so on, all these things. And then that's what you're going to write, and then calculate what are these L's and U's, and that is going to be, will it come out to be the same as what you have obtained from the Gaussian elimination. Okay, so that is the second problem. It's just that it is a 4 by 4 matrix. Okay, that should be anyway straightforward because it's only 4 digits. Okay, so that is the second problem. The third problem is with respect to multiplications and then Gaussian elimination. Okay, so those are the two hand calculations which carry 25 points each. Then coming to the programming part, we have I asked you to write a program that performs Gaussian elimination for the square system of size n by 1, n by n. Consider writing it as a modular program with separate functions or subroutines that perform forward elimination and backward substitution. To test the program, solve the system Ax equal to b. So essentially, whatever is the algorithm that we have learned in the class, you are going to code it up as much as possible. Use write it in a modular way. That means use some functions and then write it in MATLAB or C, whatever you like. I think most of you will be working with MATLAB. Then I given you a system to solve, that is Ax equal to b, in which Aij is now defined using max of I comma j. That means your matrix A is going to look like, let us say this is row 1, column 1, 2, 3, 4, and so on. This is row 1, 2, 3, 4, 5, and so on. So it is basically max of ij. So it will be 1, max of 1, 1, max of 1, 2, 3, 4, and so on. So it's going to be 2, 2, max of this is 3, and so on. Okay, that is how you will going to populate the matrix. So that is your matrix A. Once you have matrix A, and the right hand side is B is all 1. So this is all 1 vector. Solve the system to obtain the solution vector for, I have given you several n values, 32, 128, 512. But then you see if you are able to do 512, you do it. Otherwise, you do 32, or maybe you can even do 16, 32, 128, 256. See whatever 3 values you can do, okay, depending on how much time it takes to run. Then I ask you to plot a graph between n and 1 divided by sigma xi. That means you're going to get the solution vector x, okay? Sum all these component values, that is your sigma xi, I equals 1 to n. Then 1 by sigma xi, you plot that versus n, okay? So on the x-axis, you can plot n value, that is equal to 16, 32, 128, whatever. And then on the y-axis, you plot 1 by sigma xi, okay? So that's going to give you some graph. So that's what I wanted to ask you to plot, okay? So that is simple check that the solution, what is the solution and how does it look like with changing the number of rows and column of the matrix, size of the matrix, okay? So that is about the assignment problems. Any questions on the assignment problem before we proceed to the lecture? Questions, anybody?
Sir, plotting the graph is also via programming, is it?
Plotting the graph is, no, there is nothing to program. It's just a simple plotting command. I think that is there in MATLAB. You just have to specify the vectors and it will plot.
Okay, sir.
Yeah. Because many a times once you have found some answer, it is useful to plot and visualize what is the answer look like, you know. In this case, it will be very straightforward, but in general, you should know how to plot, present it in a graphical form.
Sir, I just have another question regarding the first problem. So I just tried out in the last weekend, and yeah, I faced a similar problem. Like what happened was, like when we in this, it says the 4-digit floating point decimal algorithm. So the when I did, I got this 2,2 coordinate. The coordinate, I mean the point at the middle, turns out to be 0, and I was not able to proceed to the next step for the by using it as the pivot for clearing the third row. Yeah.
Oh, okay. So you mean in the second here, this itself will become 0?
Yeah, that also becomes 0. Yeah, correct.
Oh, I see. This also becomes 0. So as a result, then you have to, what you're saying is that you have to do pivoting.
Yeah, without pivoting, I'm not able to do, like as it says in part A. Yeah.
Can you check? That may not be correct actually. You should be able to do it, I think. Even, let me check if what I have done. I think you should be able to, I think if you do no pivoting, it will not become 0. I think it will become 0.0001 is what I got actually. Because
when I did, based on the 4-digit floating point, we get 1.667, right? Like
you get some yeah. So when you do that, you'll get a 0001 in there instead of 0.
Okay.
You may verify it once, okay?
Yeah. Okay.
Yeah. So it will not be 0, it will be some 1a minus 4, okay? 0.0001. Yeah. Yeah, so it will not become 0 actually. Just check it, okay, once.
Yeah. Okay.
You have to apply this round off with 4 digit at every operation. That means every division, every multiplication, and so on.
Yeah.
Yeah.
Understood.
Yeah. Other questions? Anybody? Has anybody given it a try?
Sir, when we do this round off, will it be 0.0001 or 001, sir? Because we are having 3 decimals after here, 1.667. And the other number what I got was 1.666.
1.666 and 1.667. Not 1 point. I think it will be. You'll get something like 0.6667, 667, and 0.46s.
Oh, okay, sir. Okay. Sorry.
Yeah. So that's going to give you 0.0001 actually.
Okay, correct, sir.
Yeah.
Okay.
Yeah. Okay. Any other questions, anybody? Shall we proceed with this? Oh, okay, fine. So let's get started. Okay, so let's get started with the lecture. Are you all able to install MATLAB?
So still we have difficulty in installing, like so we contacted help desk, but still it is being open with us.
Still it is giving?
Like the help desk has to resolve that concern. It is still open, the concern is open with help desk.
Oh, I see. Installation, you have the VPN access, no?
So maybe just one suggestion here, like the online MATLAB, we can sign in with our S-mail ID, and that is actually working.
Oh, I see. Okay.
So we don't have to install MATLAB in our PC. The online version works, and I also tried out the assignment problem.
I see. Okay. So I think for those of you who are comfortable installing, you can install. Otherwise, you can use the online version with the S-mail. That is also, I think that is a good suggestion. Hopefully, it is not too slow when you run it. Then you can run it on the MATLAB server itself.
Yeah, it was quite good. Yeah.
Okay, that's good. Then I think there is no need to install. I think then you can use any kind of fast, slow computer and then run with that. Okay. Let's get started. Any other questions? Please feel free to comment or stop me. So in the last lecture, we looked at essentially we started the solution to nonlinear equations. Solution to nonlinear equations. Nonlinear algebraic equations, right? That's what we are looking at. Okay, and we said there are different methods. The first one is the bisection method that we have already seen. Bisection method. So we looked at how the method works, and then we looked at the algorithm. Then we wrote a pseudocode, and then did some problem with it, and then looked at the rate of convergence. Okay, now let us look at the next method, that is the Newton's method. Okay. Newton's method is also known as in the literature as Newton-Raphson method. Newton-Raphson method. So Newton's method is kind of a very popular method because it has applications in the solution of differential equations as well as in integral equations. Okay, and also Newton's method can be extended to not only it can be used for a solution of nonlinear equations, like it can be extended to solution of system of nonlinear equations. So system of nonlinear algebraic equations can also be solved using Newton's method, which is basically a more generic version of what we're going to see, that we will see anyway later when we come to the solution of systems of nonlinear algebraic equations. Okay, so now before going into the algorithm, let me just explain how does Newton's method work. So Newton's method is going to basically deal with, so we have some nonlinear function. So let us say that is my x and y, and then we have some function. Let us say my function is something like this, okay, something like this, and then we are interested in calculating what is the zeros of this function. So this is basically my f of x, and this is my x. I want to calculate what is this root, this is the root r. Okay, but then just like in the bisection method, we have to give two initial guesses, right? We said a and b, or and so on, which are basically should be on the either side of the root, which we checked it using f of a times f of b. If that product comes out to be negative, we said the function is changing its sign from positive to negative or negative to positive. As a result, there must be some root in between x equal to a and x equal to b. Whereas in the Newton's method, unlike the bisection method, you just need to start with one initial guess. You just need one initial guess, and that initial guess is let us say some x naught. So you provide some x naught, and then for this x naught, you're going to calculate what is f of x for this x naught. Okay, so let us say that is your f of x for this f naught. So this is f of x naught. Okay, then once I calculate the f of x naught, I'm going to let me say, okay, let me say for this x naught we have f of x naught. That's what I have done here. Then I'm going to draw a tangent to this function at x naught. Okay, so that's going to be basically a tangent is going to be look like let us say that's not a tangent yet. Okay, so let's say that is a tangent that's going to look like that. Okay, that tangent is going to cut the x-axis at some value. Okay, let us say that value is x1. Okay, so that value is x1. So this is x1, and then at x1 I'm going to again evaluate what is the value of the function. Okay, that's going to give me what is f of x1. Now again at f of x1 I'm going to draw a tangent. Okay, I'm going to draw a tangent. Let me try to draw it like this. Okay, so I'm going to draw a tangent again. That's actually taking me to the other side. Okay, let me say it is somewhere intersecting somewhere here. This is my x2. Okay, now I have to define my function again. Okay, let us say my function is something like that. So at x2, I'm going to again calculate what is the f of x2. So this is my f of x2. And at here, I'm going to draw a tangent again. Let us say this tangent goes like that. Then I get to next point called x3, and then I calculate what is f of x3, and so on. I keep doing this thing until I zero on the root. Okay, so that is the idea. That means we're going to start with one initial guess, and then we're going to draw a tangent to the curve that is f of x at x naught, and then we're going to assume that the root of the function is actually the root of the tangent. That means wherever the tangent cuts the x-axis, we say that approximately this is the root. But then we realize that because I have replaced the function with just a tangent, which is basically a linear function instead of this nonlinear function, I know that what I'm getting is, although it is the root of the tangent function, it is not exactly the root of the function that I am interested in. So as a result, I'm going to do an iteration on it. Again, look for what is f of x1, and then I'm going to draw another tangent there, and so on. I'm going to continue with a hope that eventually it's going to converge to some root. Okay, so that is the idea. Okay, so that is the idea. Now, how do we put this in? How do we explain this thing? That means I have this function. So that means we say that in Newton's method, the tangent is assumed to locally define a root, right? That means we are using the tangent function instead of the instead of the given function itself, okay, to determine the root. That means what we're saying is that in the neighborhood, so in the neighborhood of x naught, so in the neighborhood of x naught, what we say is that the function f of x naught is represented very closely with the tangent. Okay, that means I can write my L of x, which is the tangent, as f of x or f of x naught plus f prime of x naught times x minus x0. Okay, so this is the equation of the tangent, and this is a this tangent is a good approximation to the function, f of x in the neighborhood of x naught. Okay, that's what we're saying. Now, how do I determine this this tangent? Essentially, that is the equation of this line. So this is the equation of the tangent. This is the equation of the tangent that we are interested in. How did we get that? We essentially got it from the slopes of this function, right? So if I can write this, I can write this as the slopes are the same, and then I can get what is L of x, right? So essentially, this is nothing but yeah. So essentially, the slope is nothing but of this function is nothing but f prime of x naught, that is equal to L of x minus x naught divided by x minus x naught, right? So that is how I have obtained the equation of the tangent from the slope. Now we say that this is basically a approximation to the function. So I can calculate the roots of this tangent are going to be a better guess for my root of my function. That means I want to look for where is L of x equal to 0, right? That is the root, because I want the tangent to cut the x-axis, and we say that may be my root. Okay, but we know that is not the root actually, right? But that is just a better guess for the root, or it goes towards the root from the initial guess I have. When this process can be repeated, that means if I set LHS equal to 0, what I get is f of x naught minus f of x naught equals f prime x naught times x minus x0. That means I can write my x equals x naught minus f of x naught divided by f prime x naught. Okay, so this is my new guess. Let me call it as x1, and then we're going to repeat this process. We're going to draw successive tangents and then come up with new roots. That means we're going to say x2 equals x1 minus f of x1 by f prime x1. Similarly, x3 equals x2 minus f of x2 by f prime x2, and so on. Okay, so that is how we're going to repeat the calculation until the process, until the solution converges to a root, okay, to something, okay, essentially after several iterations. Okay, so that is the method. Now, of course, Newton's method can be thought of in multiple different ways. This is one way to think about this thing. So an alternate way to describe or to understand Newton's method is basically, let us say I have this function f of x naught plus I know that f of x naught is equal to 0, but then I want to correct the x naught, the initial guess, with some h value, which will basically make it the function value equal to 0, right? I want to calculate the root of the function, so I want to correct my initial guess x naught with some h, so that this is equal to 0. But then this is right now not equal to 0. But then what is the correction I should make to x naught so that I'll get the root r? Okay, that is the idea. Then we can use Taylor series expansion. Okay, assuming that the h is small enough, we can expand f of x naught plus h equal to f of x naught plus h times f prime x naught plus h square by 2 times f prime x naught plus and so on, h square by 2 factorial, h cube by 3 factorial, f triple prime x naught, and so on. Okay, so that's what we're going to see. And then we're going to set this value, of course, equal to 0. That means what we have is we have 0 equals f of x naught plus h times f of x naught plus h square by 2 factorial f double prime x naught, and so on. So what you see is that unlike the bisection method, we realize that in the Newton's method assumes that the function f of x is differentiable, and it has a continuous slope, right? It means it is continuously differentiable, is what this Newton's method assumes. So as a result, because I'm using f prime x everywhere, right? Because even in the method I have derived, I have used f prime x. So now we know that we want to set this equal to 0. That means I want to calculate h such that this particular equation is satisfied, right? But then this is very difficult to calculate, right? Because now I have to calculate just one h value that satisfies this entire equation, which is difficult, right? Because I have a polynomial equation for h, and then I have only one equation, so I cannot determine. So as a result, I make an assumption that I'm going to consider only the first two terms of the Taylor series expansion. I say that these are small quantities. So as a result, my h equals minus f of x0 divided by f prime x0, right? That's what. If I set these two terms equal to 0, I'm going to get an expression for h as minus f of x0 divided by f prime x0. Okay, that means then I can make my correction, that is x0 plus h, as my new value, that is equal to x0 minus f of x0 divided by f prime of x0, right? So that is nothing but again the Newton's method, which we have derived previously by assuming the tangent as the approximation. The second method way of looking at is the Taylor series expansion method. Okay, so these are two different ways to think about Newton's method. Now, of course, again, what we will show a little later is that not only the function f of x is differentiable and it is continuous in f prime x, we also say that it is also continuous in, it has a continuous second derivative. That means the second derivative is also exists. Okay, so continuous second derivative. Okay, so that is what we say. So as a result, so this we will say in the case of, we're going to use this result in the case of error convergence or error estimation or the convergence analysis, which is going to come a little later. Okay, in the convergence analysis. Okay, so is the method clear what we are trying to do? If this is clear, we'll proceed to calculation of a simple problem. That means essentially what we are saying is that we are saying in the limit. So that means in general, I can write xn plus 1 equals xn minus f of xn divided by f prime xn, right? That is my iterative formula for Newton's method. And then in the limit of n tends to infinity, my xn is going to reach the root value. Okay, so that is it converges to the root under favorable conditions. Okay, favorable conditions. Okay, yeah, any questions before we try to solve a problem with Newton's method? No questions? Is it clear?
Clear. Yes, sir. Clear,
Okay.
sir.
Okay, good. Okay, good. Let's then try to solve a problem, but then I need your help to evaluate what is f of xn and f prime xn. So calculate, so essentially given function is, so this is, let us say, example problem. I have a problem here. This is f of x is given as some x cube minus 2x square plus x minus 3. Okay, that's what is given. The initial guess is given as x naught equals 3. Okay, that is what is given. Now we need to calculate what is the root of this function. Okay, calculate the root of this function. Now, of course, I need your help in calculating this thing, and then we can calculate what is f prime x. F prime x equals 3x square minus 4x plus 1. Okay, that's what we have. Then I need, I would make a table just like before. So essentially, this is the n, that is the iteration number. This is xn. Then we have f of xn, f prime xn, and then my xn plus 1, I know that is equal to xn minus f of xn by f prime xn. Okay, that's what we have. Okay, so that means first iteration, my initial guess is 3. What is f of xn? I think I would need your, I need you to use calculator or something and tell me what are these values. F of xn is 3 cube, right? 27 minus, this is going to be 18 plus 3 minus 3. 27 minus 18, this is 9, is it? Okay, this is 9. And then f prime xn is going to be 3 squared, this is 27 minus 27 plus 1, 28, 28 minus 12, right? 27 minus 12, that is 15, huh? Okay, 16. 27 minus 12, this is 15. Okay, fine. Then what would be the, in the second iteration, what is xn plus 1? Can somebody calculate what is fn by fn prime and then calculate what is xn plus 1? How much will that be? That is 3 minus 9 by 15. How much?
It should be 16, sir.
It should be 16.
16, huh? Sorry, 16. Okay, 16. How much was it? This is 27. Oh, 28. Okay, 28 minus 12, 16. Fine. Okay, good. And how much is going to be the xn plus 1?
4.
4, is it?
Yes.
No, it's not be 4, right? This is 3 minus 9 by, should be less than 3.
Yeah.
Sorry, sir.
Yeah. It'll be some 2 point something. So I want you to code up these values in your calculator. X cube minus 2x squared plus x minus 3. And then someone else can do the f prime so that we have these two values. Okay. So what is xn? Xn plus 1? 2 point?
4375. 2.4.
2.4375. Okay, then f of xn for 2.4375. You can write in a calculator what is this value, right? X cube minus 2x squared plus x minus 3. Let me get my calculator. Okay, so we have alpha a cube minus 2 times alpha a square plus alpha a minus 3. Okay, calculate. You want 2.4375, right? That is 2.037. 2.037. F prime xn, anybody? It's going to be 9.074. Okay. Then what we have is we need to calculate what is xn plus 1. 2.4375 minus 2 by 9. Okay. 2.037 by 9.074. How much would that be? Anybody? That will come out to be approximately 2.213. Okay. And if I calculate for 2.213, that's going to be 0.256 would be fxn. 0.256. F prime xn will come out to be 6.84. Okay. 6.84. Then I can calculate what is the next xn plus 1. That will come out to be 2.176. Okay. And I put in 2.176, that's going to give me, already this is going to be 0.00936. Okay, you can see that fxn is already almost very small. F prime xn is 6.5, and then we can repeat the process. Okay, so you can repeat the process if you want. So essentially, you can see that f of xn is already 0. The after you do several iterations, the solution will come out to be 2.17 455. Okay, I have solved it before, and till for an f of xn of 10 power minus 6. Okay, so that will be the root, okay, which you can continue. And how do you check the error in this case? Error, you can check it from your either f of xn, or you can check, either you can use f of xn to check for error, okay, or you can use the delta, that is basically f of xn by f prime xn, right? Because this is the delta, right? This is equal to nothing but your xn plus 1 minus xn is equal to minus of this, right? So we can even use this value to check for, if this change is small, then we can say that xn plus 1 is very close to xn. As a result, I have reached some kind of convergence. Okay, we can do that as well. Okay, so I think all of you will be able to do Newton's method easily. Okay, so let us try to write a program for Newton's method. So let us write a pseudocode. Let's say subroutine or function, subroutine, Newton's method. Newton method. What all we need to pass? We need to pass f, the function. We need to pass f prime, the derivative of the function also, right? This needs to be coded up somehow. And we need to pass what is the initial guess. I just need to pass what is x, that is the initial guess. I need to also pass how many maximum number of iterations I want to do. What is the tolerance I want to kind of converge to, right? So that is what I need to pass. Then as soon as I enter, I can calculate what is f x equals f of x, right? So I have passed the function, I have passed the initial guess, so that is my fx. Then I can print to the system, print out 0th iteration for x value. This is the f of x value, right? So I'm printing out the iteration number x value f of x. Okay, I do that. Now, once I print this thing, I can do iterations. I essentially do I equals 1 to number of maximum iterations. Okay, so I'm kind of starting some loop here. Then the first thing I'll do is that I need to calculate what is f prime x. That means I'm going to calculate what is fx prime equals f prime of x. Okay, that means I have already f of x calculated. F prime x is what I need to calculate. And if my fx prime comes out to be too small, let us say if my absolute value of fx prime is less than the tolerance, right? That means if it is very small, okay, this tolerance could be different for convergence and for this one. Okay, this is basically some checking for the slope tolerance. Okay, slope tolerance, this can be different. Then if the slope is too small, why am I interested in calculating the slope to be too small? Why am I interested in checking for that? Because if this slope comes out to be too small, then what will happen? You have a division by approximately division by 0, right? Or some value by 0, which is going to give me my xn plus 1 to be very large value, right? Because I'm subtracting a very large value. So that means then what we say is that if this is the case, then we say print the slope of the function is too small, right? Print the slope of the function is too small at x. Okay, and then we're going to return or exit this, and then otherwise we're going to come out, right? So if this is the case, we're going to do that. Otherwise, we're going to once fxp is known, then I can calculate what is my delta. Delta is the change equals minus fx by fx prime. Okay, so this is much simple code than what we have written for the solution of systems of linear equations. So once I have the delta, I can calculate my xn plus 1 equals xn minus or plus delta. I have used minus here, so I can use plus here in the next step. Okay, so my xn plus 1 equals xn plus delta is what I would do. Then I have the new value. What should I do? Then I can check for convergence, right? If my delta, right, the absolute value of delta is less than tolerance, then I can say print solution converged in n iterations, right? I'm going to print what is I for that, n is I'm going to be I iterations, and then the solution is essentially print the solution as iteration I, x, and then f of x. Okay, but I have not calculated what is f of x. Okay, so I'll just print. Okay, it will be very approximate, so I think that is not a problem. Then I'm going to do end if. Okay, then what should I do? Then when I go back, I need the new f of x. Okay, so I can even calculate. So after this, I can calculate what is f of x equals f of x. Then this will also be updated. Then I'm done with this thing. Then I'll say end do. Okay, that closes the do loop. And then I can say end subroutine, right? This is basically my end subroutine. Okay, that is a very simple algorithm, right? Which you can easily code up for Newton's method. Okay, any questions so far on the Newton's method or on the program?
Sir, clear, sir. Clear, sir.
Clear. Okay, very good. All right. So then let's move on to the convergence analysis. Okay. So so we have in Newton's method, the new iteration is xn plus 1 equals xn minus f of xn by f prime xn, right? Let me also define what is my error at any step as en as r minus xn. Okay, that is the error where r is the root, xn is my value of the root, or the running iteration value, and then at any iteration number n, my error equals r minus xn. Similarly, error at n plus 1 is going to be r minus xn plus 1, because my root is the same, whatever I'm trying to solve, only my xn is changing from xn plus 1 and so on. Okay, so that is what is changing. So that's going to be r minus xn plus 1. Fine. So then what we have is I can now define what is f of r. F of r is essentially equal to 0, right? Because the value of the function at the root is equal to 0. But this can also be written as, r can be used as en or xn plus en, right? I can write this as r equals xn plus en, right? And again, this can be expanded in Taylor series as f of xn plus en f prime xn plus en square by 2 factorial f double prime xn plus and so on, right? So I can expand like this. But then I know that on the left-hand side, this quantity is actually equal to 0, because this is f of r, which is equal to 0. That means I can write here what is the value of, what is this value? That is basically f of xn plus en f prime xn equals minus en square by 2 factorial f double prime xn, right? So this is one result I have. Okay, so that is one result I have. Then, okay, then I'll go back to my definition, which is this one. Okay, xn plus 1 equals xn minus f xn by f prime xn, which is xn plus 1 equals xn minus f of xn by f prime xn. And then I'm going to subtract this equation from r, the root r. Okay, that means r minus xn plus 1 on both sides. So this is going to be r minus xn plus f of xn by f prime xn. Okay, that's what I have done, which is going to be, what is this? R minus xn plus 1 is my error at n plus 1. Similarly, r minus xn is my error at n, plus I have f of xn by f prime xn. Right? That's what I have. That means I can further write this as en plus 1 equals, if I multiply this and kind of simplify, en f prime xn plus f of xn divided by f prime xn. Okay, that's what I have. But then what is f of xn? What is the value of the numerator? F of xn plus en f prime xn. I have just obtained this as f of xn plus en f prime xn as minus 1/2 en square times f double prime xn. So I can substitute from there. Okay, so from let's call this equation A. So from equation A, I can write my En plus 1 as minus 1 by 2 En square f double prime xn is the numerator divided by f prime xn is the denominator. Okay, that means what I have is En plus 1 equals minus 1 by 2 f double prime xn divided by f prime xn. All this is multiplied with En square. Okay, so I have some factor here which is En plus 1. Let me call this as some C of delta times En square. Okay, where the C of delta is actually is less than 1 only in the neighborhood of the root. That means if you, as you get very close to the root, this C of delta is less than 1, which basically tells you that the error in the next iteration, that is En plus 1, is the error in the next iteration is actually decreasing as a square of the error in the previous case, right? These errors are less than 1. That means the convergence of error in Newton's method is actually quadratic. Now this is very nice because the bisection method, the decrease in error was only linear, right? It was only decreasing, in fact, half compared to the previous iteration, right? So in the bisection method, what we saw was bisection method En plus 1 is only equal to 1/2 En, right? That is very small, right? You have to take a very long time to get to the error tolerance if you are doing iterations. Whereas here it is quadratic. Okay, it is decreasing as En square. Now what does this mean? Let us say if my En can be represented as 10 to the minus k. Okay, what do I mean by 10 to the minus k? That means my En is actually r minus xn. That means my r is something, my xn is the guess value, is the iterate value that I have in this thing, and then this difference between these two, I'm writing it as 10 to the minus k. Okay, that means r and xn are matching up to the kth decimal, right? That means only in the k plus 1th decimal they are differing by, let us say, 1 unit. That means if I have, let's say, if I take k as like 2 or 3 digits, let's say if my r is 2.35212, let us say if I take k equals 3 or something, right? That is 10 to the minus 3. My xn would come out to be something like, let us say, 35205 or something. Okay, so it matches up to 3 digits. Only in the 4th digits they are differing, right? That's what this means. But then what would be, if this is the case, what would be the error I will get if I solve this using Newton's method in the next iteration? That is going to be En square, like C delta is less than 1. So C delta times En square is going to be 10 to the power minus k square. That means this is going to be of the order of 10 to the minus 2k. That means En plus 1, by definition, this is r minus xn plus 1. That means my new xn plus 1 is going to differ from r for 2k digits. So it's going to match for 2k digits, 2k digits, and then it's only going to differ in the 2k plus 1th digit, right? Till then it's going to match. That means the error in the En plus 1 has twice as many correct decimal values than En. That is kind of remarkable because you are able to converge it in a quadratic way. Okay, so that is the power of Newton's method. However, Newton's method is also prone to several issues. Newton's method is prone to several issues. Several problems, and its convergence is not guaranteed. So not guaranteed to converge. So we will see under what conditions or circumstances this will not converge. As a result, Newton's method is always used in conjunction with bisection method. In conjunction or together with connection with bisection method. Okay, that means what are we going to do? If you take any software such as MATLAB or anything else which can find which can do root finding, you're essentially going to run bisection method. So you're going to run bisection method for several iterations. Let us say you run bisection method some 10 iterations. Then you're going to get very close to the root or close to the root, or we can say just close to the root. Then you're going to run after this Newton's method. Okay, because once you are in the very close vicinity of the root, Newton's method will converge in a quadratic way. Okay, and it's going to converge very quickly in terms of decimal. That means if where you want very good precision for the root, then you're going to use a combination of bisection method plus Newton's method, because bisection method would take much more longer to converge to the correct number of digits you want, whereas Newton's method is very fast in that sense. So you're going to use a combination method, that is run bisection method for several iterations, some 10 or 12 iterations. Then you get close to root, then you run the Newton's method, okay, which is going to give you very close to the root values to as many digits as you want. So that is how usually the Newton's method is applied in conjunction with the bisection method. Okay. Now there are some cases in which Newton's method would not work. I'm going to discuss them, but before that, any questions so far? Any questions so far? No?
No, sir.
Yeah, okay. So I think then this is pretty clear today. All right. Okay, fine. I think we are out of time. I'm not try to squeeze in now. So we have a few cases where Newton's method will not work. So that's what we're going to see tomorrow's lecture, and then we will look at another method, that is the a variant of Newton's method. It's called secant method. Okay, we look at the secant method and then the limitations of the Newton's method and the secant method in tomorrow's lecture. Okay, so let us look at limitations of Newton's method, and then another method that is known as the secant method in tomorrow's lecture. Okay, so once we do that, then we finish solution to nonlinear algebraic equations. Then we have to go for solution to system of nonlinear algebraic equations. Okay, fine. So with that, I'm going to stop here. If you have any questions, please feel free to ask me now. Okay.
Sir, am I audible?
Yeah.
Sir, any tentative schedule on the mid-sem?
I think it is uploaded on the.
It's in November, sir. I checked the website recently.
Yeah, I can check it. Yeah, I think it is already uploaded.
Initially, in the calendar, there was something called as the quiz. For that reason only, I just wanted to know. Quiz will not be part of our evaluation method, right? So.
No, we'll have only a midterm and a final exam. Correct. We'll have a midterm and a final exam, because quiz will be. I think I think that is better in terms of you'll get a little more time to write the.
Yes, sir.
Yeah. I think it is exam dates. Yeah. So midterm will be on 16th of November.
Noted, sir. It's as per calendar then. Thank you.
As per calendar. Yes.
Thank you.
Thank you. Yeah, I think the lecture, I was told that the videos are not recorded in the, not uploaded in the Google Drive. I'll check with the code office and then make sure it is uploaded.
Sir, yesterday when I checked, only last Wednesday's class was not available, sir. Until then it was available.
Sorry. Only last Wednesday's class was not there, huh?
20th, I was not able to see the recording for 24th, I guess.
24th, okay.
Yesterday.
Other things are there otherwise?
Let me just shortly confirm, sir. I'm just
okay. I'll anyway let the code office inform them that please upload all the videos to the Google Drive link as well. I think they are there on the portal, but not on the Google Drive link.
Yes, sir. Yeah. It is not available on the Google Drive, sir, because for 23 batch, we are not having this portal functional for the last 2 years. So For us, it is only 7 lectures that has been uploaded. So including today's, we need to have 3 more of lectures. Sir.
3 more lectures. Yeah.
Yes,
I'll inform them. They'll upload it sooner. Okay.
Sir, in the meanwhile, I just checked. It's only until 23rd the lecture is uploaded. On the
Okay. Oh, until 23rd, huh?
Yes. I'm just looking at the live session recordings tab of the portal.
No, portal is fine. Portal has all the recordings, but Google Drive doesn't have.
Yeah.
23rd was the last Wednesday, right?
Yes, sir.
22nd.
24th was also there, right?
Yes, sir. Yes. 24th.
Yeah, I'll inform them. Yeah.
Yes, sir.
Yeah, sure. But I think the lecture notes, all of them are there, isn't it?
1 second.
Yes, sir.
I think lecture notes, all 9 are there. Yeah.
Yes, yeah, all 9 are there, sir.
Yeah. I'll inform them to get it uploaded. Yeah.
Sir, and the exam will be online, sir. The midterm exam
will be online. I think it will be online. Online in the sense they will proctor it online, but you probably will write it on pen and paper and scan it and email, something like that.
Okay.
Yeah, sir. We had done it previously that way. That we'll do the same thing, right? Yeah.
Sure. Yes, I think that is better because instead of setting multiple choice questions, it is better if you write on pen and paper, because then I can give you partial marks and all those things.
Noted, sir.
Yeah.
Thank you, sir. Thank you.
Yeah. Thank you, sir.
Thank you.
Yes, sir.
Okay, guys, I want to stop here. Thank you. See you tomorrow at 4 o'clock.
Yep.
Thank you.
Thank you, sir.
Thank you. Thank you. Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you.